All right, welcome to Chapter 12. We'll talk about alkenes, alkynes, and aromatic compounds in this chapter. So we're building on that foundation we have from last chapter where we discussed the alkanes. In this first section of Chapter 12, we'll focus specifically on the alkenes and alkynes, and you'll see they're very similar to the alkanes, although the alkenes will have one or more double carbon-carbon double bond, and the alkynes will have one or more carbon-carbon triple bonds present. Last chapter, you may have heard me refer to the alkanes as saturated hydrocarbons. Well, now when we move into alkenes and alkynes, we're talking about unsaturated hydrocarbons. So what we mean by that phrase is that these hydrocarbons do not have the maximum number of hydrogen atoms that could be attached to each carbon atom. So if we're looking at the alkenes specifically, we have carbon-carbon double bonds, which could be additional carbon-hydrogen single bonds in alkanes. Now that we're in alkenes, these unsaturated hydrocarbons have at least one carbon-carbon double bond. If we move on to the alkynes, now we have at least one carbon-carbon triple bond, and each of those carbon-carbon triple bonds, of course, would possibly be two carbon-hydrogen single bonds on each of the carbons participating in that. So what we can expect for these alkenes and alkynes is we can expect to see the carbon to hydrogen ratio decrease compared with our straight chain saturated alkanes, where we saw the trend that a straight chain saturated hydrocarbon, an alkane, would have a formula of CN H2N plus 2. Well, when we're losing some of those hydrogens to make the carbon-carbon double bond or triple bond, we'll see that we have fewer hydrogens present relative to the number of carbons present. Because these unsaturated hydrocarbons could theoretically have more hydrogen atoms attached, one of the key reactions they'll undergo is reaction with hydrogen gas to form saturated hydrocarbons. Ultimately, if you have enough hydrogen gas and you have the right conditions, you can fully saturate these alkenes and alkynes. And if you've paid careful attention to your food labels, you've probably seen partially hydrogenated vegetable oils, and we'll talk about that more when we talk about lipids. But hydrogenation is a very useful reaction, and it relies on double bonds or triple bonds. Hydrogenation can reduce those to ultimately single bonds with hydrogen. Focusing specifically on alkenes, again, alkenes will have at least one carbon-carbon double bond between adjacent carbons. They're flat or planar because these atoms in the double bond lie in the same plane. In order to participate in what we call pi bonding, that multiple bond relies on p orbital overlap. So in order to get the px on carbon 1 to overlap with the px on carbon 2, for instance, they both need to be in the same plane so that the px orbital on carbon 1 and the px orbital on carbon 2 are appropriately aligned for side-to-side overlap. Therefore, wherever you see a carbon that participates in a single multiple bond and then two single bonds for an alkene would have a trigonal planar arrangement around those carbon atoms involved in the double bond. Back in the alkane chapter, you probably remember each of the carbons was a tetrahedral, 109.5 degree bond angle. Here, the trigonal planar arrangement of the carbons involved in a double bond would be a 120 degree bond angle. Now, hopefully you've noticed on the past couple of slides we've had this chemical structure of an alkene, ethylene in particular, on the right-hand side. Ethene, as it's officially known by IUPAC naming, or ethylene is its old common name. Again, you're going to see both a lot. You're going to see that common name probably as much as the IUPAC name because, as I've lamented in the past, these common names persist. These are what the older chemists were taught, and they're what the older chemists teach to the younger chemists. So because you'll see it, I teach it, but again, it would be great to move to IUPAC only naming and just seeing ethene, but truth be told, you're going to see ethylene, and you've probably already seen it in things like polyethylene, which is a polymer based on ethene or ethylene, and therefore it no longer has its carbon-carbon double bond because in the polymerization process it's made carbon-carbon single bonds. But back to the case at hand, ethene has the chemical formula of C2H4. So notice it's C sub n H2n in this case, and that's for any straight chain alkene is you're going to see a CnH2n. That could confuse us with the cycloalkenes, if you remember, because the terminal carbons rather combine to close the ring, we ended up losing 2 hydrogens. So you have to be very careful if you're given a formula CnH2n because you need to consider not only if it's an alkene like ethene, it could also be a cycloalkane. So you'll have to look at some other information and not make a judgment call too quickly based only on chemical formula. Alkanes with that straight chain ratio of CnH2n plus 2, that's a giveaway that you have a straight chain alkane. But again, CnH2n could be a straight chain alkane, it could be a straight chain alkene rather, or a cycloalkane. In this case, ethene has 2 carbon atoms, and they're connected by a carbon-carbon single bond and then a carbon-carbon double bond. Each of the carbons can make another 2 bonds, right? We said in our course carbon's going to make 4 bonds, so each carbon's used up 2 bonds in that double bond. That means each carbon has 2 remaining bonds that they can make, in this case with hydrogen atoms, for a hydrocarbon like ethene. It's flat, it's planar, because all the C and H atoms have to lie in the same plane to get the right bonding overlap. One application of ethene is to accelerate the ripening of fruits. It's a strange molecule for fruit ripening, but that's what the fruits naturally release and ripen with, so we can use that artificially by increasing the amount of ethene in the atmosphere around the fruit and cause faster ripening. Okay, moving on to the alkynes. Now, of course, we have at least one carbon-carbon triple bond, and that requires the 2 carbons engaged in that triple bonding to have sigma overlap, if you remember that type of overlap from Chem 141 or whatever prior chemistry, general organic biochem 1 course you had. In the general chemistry part, you likely discussed bonding, and so the sigma style bonding is the hybridized orbital overlap, in this case sp and sp head-on overlap. That's what keeps the 2 carbon atoms together in the first place. Then as we discussed for the alkenes, you'll have p orbital overlap, so maybe the px and the py will overlap here. So you'll have 2 types of side-to-side pi-type bonding, p orbital overlap, and that requires a very close connection between those 2 carbon atoms. That's a very short bond distance to get the overlap in order to have the sigma-style hybrid orbital lap in this case, and then also 2 pi-type side-to-side overlaps. In the case of alkynes, wherever you have that carbon-carbon triple bond, you're going to have a 180-degree bond angle around those, and they'll have to be linear in terms of geometry about those carbon-carbon triple bonds because of the need to keep 2 p orbitals unhybridized, and then therefore your hybrid orbitals are sp hybrids, and they'll have 180-degree bond angles. All right, so hopefully you noticed in the previous slide that we had ethyne visible, that chemical structure of C2H2. It's also known as acetylene, and this time you're going to see acetylene a lot more, the common name, unfortunately, a lot more than the IUPAC name. Ethyne obviously tells us it's an alkyne if you catch on to those endings, whereas acetylene doesn't. Acetylene looks like it's an alkene by that IUPAC ending, so just be very careful. Just like we had ethylene, instead of ethene being a common name that's prevalent, acetylene is even more prevalent, and you'll be unfortunately very shocked to see ethyne anywhere out in the world, because the organic chemists almost always refer to it as acetylene still. So it has the formula C2H2. It has that carbon-carbon triple bond, which is why when the carbon atoms each make 4 bonds, they have just 1 bond left to make with a hydrogen. It reacts with oxygen in a combustion reaction that produces a very high temperature, above 3,300 degrees Celsius. So that's a very hot reaction, and as a result, its major application is in welding. So acetylene torches are very common. Welders use them all the time. You'll probably see the acetylene tanks if you ever have to have anyone do any welding at your house or go and get anything welded professionally. So there it is, a very useful gas, and therefore because it's been useful and it's been in use a long time, its common name of acetylene tends to predominate. But officially the name that we would call this in our course is Ethyne. It is indeed an alkyne, and Ethyne is a name that reminds you of that alkyne nature. Let's pause here for a learning check. Make sure that you're getting these distinctions between alkane, alkene, and alkyne down. So on this learning check, you're just going to identify each of these structures as either an alkane, an alkene, or an alkyne. Pause the video here while you make those assignments. Once you've decided which class each of these 4 structures belongs in, then start the video back up and we'll see how you did. Okay, so hopefully that went pretty well for you. I'm guessing the first 2 were pretty easy. A with that triple bond is definitely an alkyne, and then B with the double bond is an alkene. Moving on to C and D, notice those are those skeletal structures. Hopefully you've been practicing them. They look really neat. They'll really distinguish you as an organic chemist compared with just a person who has never seen these things and doesn't understand them. So make sure you're still working on being able to draw and interpret these skeletal structures. The first one, C, there has a double bond at the right-hand terminus, so that's an alkene. And D there, everything is a single line, so we have an alkane. If you did have trouble with any of these determinations, please try some additional end of chapter problems and certainly reach out to me if you're still struggling. Otherwise, let's move on. So we struggled with naming last chapter, and hopefully you got those conventions down, and as long as you have that firm foundation of alkane naming, then there's not a whole lot of change here for alkenes and alkynes. So just like in alkanes, we're looking for the alkane name for the longest carbon chain. And then because these are not alkanes, we're going to have to change the ending of that alkane name to -ene for an alkene, E-N-E at the end, or -ine for an alkyne, Y-N-E at the end. So here in table 12.1, we see a comparison of those 3 types of hydrocarbons. So we've got the alkane, ethane, and propane. Eth, the prefix for a 2-carbon chain, prop for a 3-carbon chain, and they're both alkanes, so they end in A-N-E. Once we move to alkenes, we now have ethene, which as I said you'll often see as ethylene, its old common name, and you have propene, which is of course the IUPAC name and also the common name, fortunately for that one, so you won't see anything else too much there. So there we have it. Eth, the prefix for a 2-carbon chain, instead of the ane in the first column, now it's an ene because of the carbon-carbon double bond. Same deal for the propene. Finally, for the alkynes, we have ethyne, but as I said, you're probably more likely to see it as acetylene. And then we have propyne for the 3-carbon alkyne. So notice the double or triple bonds are drawn into those skeletal structures, usually as a line below or above. In the case of alkynes, you'll need a line above and below to indicate the triple bond. So not too bad. Really just taking those nomenclature rules you've hopefully already gotten down and editing those endings for ENE for an alkene and YNE for an alkyne. For those of you who've become used to the guides, here's our guide to naming alkenes and alkynes. So first, just like our guide to naming alkanes, we named the longest carbon chain that contains the double or the triple bond. Now notice the deviation here is that we're looking for the longest chain that contains the double or triple bond. In the alkane case, we were just looking for the longest chain. So be careful, we have to contain the double or triple bond. It is indeed a functional group, as we talked about at the last lecture of the previous chapter, and in order to show the priority, the importance of that functional group, we need to have it in our main chain. Second step to our guide, we number the carbon chain from the end near the double or triple bond. So if it's right in the middle, it doesn't matter, but if it's further to the left, we start with the carbon furthest to the left. If it's further to the right, we start with the carbon furthest to the right. We can't just start at the carbon-carbon double bond or triple bond if it happens to be in the middle of the molecule, but certainly if it's a terminal double or triple bond, we'll know where carbon 1 is. Well, it'll be one of the bonding carbons involved in that double or triple bond. Finally, step 3, give the location and name of each substituent in alphabetical order, just like we did for the haloalkanes, as a prefix to the alkene or alkyne name. So hopefully this seems very familiar. The biggest change is that now we have a double bond that would cause us to end in ene, or a triple bond that would cause us to end in yne, and of course we need to contain that double or triple bond in our longest carbon chain. All right, so let's practice with a couple examples here. We'll write the IUPAC name for the following two structures. So we have an alkene there in A and an alkyne in B. So step 1, name the longest carbon chain that contains the double or triple bond. So we've just identified the functional group for each of those, double bond for A, triple bond for B. So the class is going to be alkene for A, alkyne for B. We'll take that IUPAC name that we would have used for an alkane and replace the ANE ending with ENE for A, and replace the ANE with YNE for B, and therefore we'll be showing that we have an alkene for A and an alkyne for B. Okay, so in A, for step 1, we see it's a chain that involves 4 carbons, so it's going to be a butene. For B, the longest carbon chain, and you have to be careful with your counting because remember that triple bond, there's a carbon at each point. So we don't have a corner to show us a carbon there. We have the triple bond to remind us that there's 2 carbons there. So if we start at the left, we have 1, and then we have the carbons of the double bond, carbon 2 and carbon 3. Then we have carbon 4, which branches off with a methyl group and a propyl group. And of course, we want to contain the propyl group, the longer group, in our longest chain of our structure, and then we'll name the methyl group as a substituent. So we end up with carbon 5, 6, 7 from that propyl group. Okay, so now we have those carbons numbered here, 1, 2, 3, 4 for the butene and 1 through 7 for the heptyne. And notice that the butene, we've also numbered it as 1-butene. What we didn't see in the example so far, when we had the ethene or the ethyne, we didn't see anything where we were numbering the double bond because those were 2-carbon containing compounds, so there's only one choice. Even when we went to propene or propyne, we didn't number the double bond or triple bond because it didn't matter which 2 you were bonding between because there were only 3 carbons. There was only one possible way to double bond or triple bond. But here with a butene, we could have had the carbon-carbon double bond between carbons 1 and 2 as we do in structure A, or we could have had them between carbon 2 and carbon 3, which would have been a 2-butene. We always number the first carbon that's participating in the double bond. The lower numbered carbon is what we indicate the double bond at. If we had a 3-4 double bond, remember that's really just not carbon 4 at all. That's carbon 1 and 2. We just need to flip the direction around. So be careful. There's 2 possibilities. You can have a 1-butene or a 2-butene if you have a single double bond in a 4-carbon alkene. For B, we see we don't hit the triple bond until the second carbon in, so that's a 2-heptyne. Okay, and obviously there could be a lot of other positions for the heptyne, but because the lowest numbering system gives us the first carbon of the triple bond being carbon 2, we identify this as a 2-heptyne. Okay, now finally moving on to step 3, our final step, we have the job now to give the location and name of each substituent in alphabetical order as a prefix to the alkene or alkyne name. For A, guess what? We were already done. There are no substituents to worry about. It's just the 2-butene that we had from step 2. For structure B, we do indeed have a substituent, right? That methyl group off of carbon 4, as we mentioned earlier. So we need to include in our name that 4-methyl substituent. So 4-methyl-2-heptyne is our correct name for that particular alkyne. So not too bad, a little bit more involved because we have to indicate the name change. If it's an alkene with a carbon-carbon double bond, it ends in Ene. If it's an alkyne with a carbon-carbon triple bond, it ends in Yne. And then, of course, we have to number and name the substituents just like we did back in the chapter on alkanes. So not too much more, and remember, we only have to worry about the number of the ene or yne once we exceed 3 carbons. Just like we had to consider the cycloalkanes, we also have to consider naming cycloalkenes. So when we name that cycloalkene, if there are no substituents, the double bond does not need a number, okay? Just because, like in the alkanes, when we had, say, a fluoro group on one of the positions, in the ring, all the positions are equivalent if there are no substituents. So it doesn't matter where we have the double bond in a cyclopentene because all the positions are equivalent. If we had multiples, then we'd have to worry about it. Likewise, if there is a substituent, the carbons in the double bond are numbered as carbons 1 and 2, and then the ring is numbered from carbon 2 in the direction that will give the lowest number to the substituent. So we see here on the slide 3-methyl cyclohexane. So we could have had what we've identified as carbon 2 be carbon 1, but then we'd count all the way around and we'd end up with a value of 5-methyl cyclohexane rather than 2-methyl cyclohexene. So be careful. We have to have the Ene ending to identify it as an alkene, and for a cycloalkene with a substituent, we also have to number all of our carbons with carbon 1 starting at the double bond carbon, and then the substituent number being as low as possible to identify the substituent position. Alright, so hopefully you're catching right on with the nomenclature and having no troubles whatsoever, but unfortunately for the average beginning student in organic chemistry, that's not the case. So let's pause here for a learning check. We'll have you write the IUPAC name for the following 2 compounds. Once you've named A and B according to the IUPAC conventions, we'll have you start the video back up and we'll see how you did. But for now, let's have you stop the video here while you work on these 2 names. Okay, so like you've hopefully gotten used to, step 1 involves naming the longest carbon chain that contains the double or triple bond. So we have a pentene for A, and we have a butyne for B. Moving on to step 2 of our guide, we'll number the main chain from the end near the double or triple bond. So we see here if we number from left to right for the pentene, that's the lowest numbering for our double bond. Again, not the substituent, but the double bond. In this case, it happens to work out both, but we always want to hit the double bond first in naming an alkene. For B, we also happen to number from left to right because our triple bond is also to the left, and again, we do have a substituent as well, and that substituent, as we see, is lower priority because if we numbered what we have on the screen as carbon 4 as number 1, we'd have our substituent in the 2 position. Here, because we've put the priority on the triple bond as we should, we don't hit the substituent until position 3. So be careful. We need to find the longest chain that contains the double or triple bond, and we need to number that chain in such a way that we hit the double or triple bond as early as possible. Okay, now finally in step 3, we're going to give the location and name of each substituent in alphabetical order as a prefix to the alkene or alkyne name. So for A, because we hit both the double bond and the substituent on carbon 2, this is going to be a 2-methyl 2-pentene, right? The double bond could have been between carbon 1 and 2 or carbon 2 and 3, but in this case, it happened to be between carbon 2 and 3, and therefore that's the 2-pentene part. For the substituent, it also happened to be on carbon number 2, so that's why we have the 2-methyl prefix. For B, we look, and again, of course, the first carbon in our lowest numbered chain that has the triple bond is carbon 1 of the triple bond. So we have a 1-butyne. It could have been a 2-butyne if the triple bond was between carbons 2 and 3, but then we couldn't possibly have had a substituent on carbon 3 there. So in this case, number 1 before the butene indicates that carbon 1 of the butene, the triple bond there, is in the 1 position, and then 3-methyl out in front indicates that on carbon 3 we have a methyl group. So it's a very logical nomenclature scheme, but it does take some getting used to for beginning students. So don't fret, don't get discouraged, and certainly don't give up, because the naming doesn't go away. You saw it in the last chapter, you'll see it in the next several chapters. So just spend the time, try the practice problems, reach out to me for help. Let's get it down and get you to a place where you're comfortable with it. And maybe the best way to get comfortable with it is to do some on your own. So far we've named structures that I've shown. Let's have you go ahead and draw a condensed structural formula, or better yet, a skeletal structure if you're really comfortable with those, for these following 2 structures. So go ahead, stop the video here while you draw the condensed structural formula for 2-hexyne and 3-methyl-3-hexene, and start us back up once you're ready to check and see how you did. Okay, so there we have it, 2-hexyne. So we look at the hex first, and we know that's 6 carbons. So you might just want to draw your 6 carbons with a single bond between each, because they're all going to need a single bond, right? And then looking at the fact that it's a hexyne and it's a 2-hexyne, we know that between carbon 2 and 3 we'll have a triple bond. So you go ahead and fill that in, and now you're ready to assign the hydrogens. Obviously the triple bonding carbons can't take on any more hydrogen. They've maxed out their bonds with the 3 bonds to each other and then 1 bond each to a neighboring carbon. But the terminal carbons can have 3 hydrogens, and the interior carbons there, the ones in the 4 and 5 position, can only have 2 hydrogens each, because they have other bonds to other carbons, 2 carbons each. So there we have it. Hopefully that's the condensed formula you found, and if you did the structural formula and you want to check that out, if you did it as a skeletal formula, you could certainly send me that, and I would be happy to let you know how you did. For B, likewise, we have a 3-methyl-3-hexene. So the first thing to do is look at that longest carbon chain. The hex prefix tells us that, again, we're going to deal with 6 carbons. So just like in A, you draw the 6 carbons. And now finally, on carbon 3, you would have the carbon-carbon double bond between carbons 3 and 4, and then the methyl group as a substituent on carbon 3. And it just makes sense when you're drawing it to draw it from left to right. But remember, if you are given the structure, you may not necessarily be able to go left to right. You may have to do some twists and turns, or start right to left for the numbering in order to get the correct name. So hopefully things are coming together for you. Try some additional practice. If that's not the case, reach out to me. But as long as things are going well, we'll go ahead and pick up in the next part of Chapter 12 with our next lecture.